So the last section we're going to look at is 5.5, and this is on graphing log functions. So we'll look at the different transformations, and I'll show you a diagram, and we'll label the A, B, C, D. We'll do a little bit of sketching by hand, and then we're going to look at formula that involves a logarithm, and it's used to predict the intensity of an earthquake. So if you ever watch the news and you hear there was a magnitude 3 earthquake or something like that, that's the formula that calculates it. So I'll give you some information, you'll plug it in, and you'll find the magnitude of the earthquake. That'll be it. Okay, so the first thing, kind of touched on this different ways throughout the week, but I keep telling you that the calculator can only do 2 bases by pressing a single button. What are the 2 bases that the calculator can do for logarithms?
10 and E.
Right, it can do a base 10 log if you press that button, or a base E log if you press that button. So what if you want to do log base 3?
You do log in parentheses 12 divided by log base 3.
Yeah, we kind of figured that out when we took something like that and we changed it to exponential form. We said 3 to what power gives you 12? That's what that means in exponential form. And then we said, well, the only problem with that is having this variable in the exponent. So we took the log of each side, and then we had something like log 3x, 3 to the x, equals log 12. And then now, because you got the log, what can you do with the x? Right, you can put it in front as multiplication. And then how would you put the log 3 on the other side?
Divide both sides by log 3.
Right. So what you end up with is log 12 divided by log 3. That's what you end up with. And the shortcut for just jumping right to that without going through the steps in the middle, that's called the change of base formula. And you can do it with either common log or you can do it with natural log. And the answer will come out exactly the same. What's important though is the x is up higher. Okay, think of it as like lined paper. The x is above the b when you write it as a log. When you use the change of base formula, the x is above the b. Okay, log of x goes in the top, log of b goes in the bottom. Okay, think b bottom. B is the base. Bases always go in the bottom. Yeah? Did you have a question? No. No? Okay. So let's say we wanted to find log base 3 of 12. You would take the log of the argument and divide by the log of the base. It's just going to allow us to jump right to this final step. So take log of the argument. Make sure you close the parenthesis and divide by log of the base. Now what's the other way I said you could type it in and it should come out exactly the same? The ln, yeah. If you take the ln of 12 and divide by the ln of 3, you will get exactly the same answer. So I would pick one of these 2 ways to do the change of base formula. I usually do the log 10 rather than the ln. But either way will work. Question on the formula? Yeah.
You said you can do it those 2, but couldn't you do it with any base log?
Technically, yes, but we need a way to type it in on the calculator. And if your calculator only does base 10 or base E, you'd have to pick one of those to use your calculator. But yes. Yeah.
Why is it called the natural log?
Why is it called the natural? Okay, you're not asking where the ln comes from. That comes from natural log. You're just asking why did they pick the term natural?
Yeah.
I don't know. I mean, the common log, I guess that's one because Base 10 is used a lot, like in chemistry if you deal with pH. That's a base 10 logarithm scale. Every time you move one number over on the pH scale, it's 10 times more basic or acidic.
And our number system is based on.
But I don't know why they use the word natural. I don't know if this like comes up in nature a lot. I'm just guessing. I have no idea. I'll have to look it up and see. Yeah.
Is it so? It's because it's log the base of e, right?
Log with the base of e is the natural log. Yep.
So then is e like something found in nature, or is it?
Well, e is named after the person that discovered that number or used that number a lot. It's named after Euler.
How did Euler discover E?
I don't know.
You had a dream.
These are good math history questions. I am not a math history expert. Yeah. I did take a class called math history and learned all kinds of things like that. So you weren't really learning math, you were more learning about like how things were discovered and stuff like that. I think I have the book in my cabinet somewhere. But yeah, I don't know. I don't know how he discovered it exactly. They're all very good questions. All right, so let's graph that. Well, first of all, is the base that they want me to graph something that I can type in without using the change of base one? No, I cannot type in base 3, but I can make it a fraction, and then I can type it in. How would we rewrite that so we can put it in on the calculator?
Log of x over log of 3.
Yep. So log of x divided by log of 3. Okay, so let's sketch it. Again, the biggest thing, be careful with your parentheses. Whenever you press log, it's going to open one. It's up to you to close it. So log x, close it, and divide by log 3. Close it. All right. And we talked a little about the domain of logs yesterday. X has to be what kind of number when you're dealing with logs? Like the thing that you plug into the log.
Integer?
You can do decimals. Decimals are okay. Positive. It can't even be non-negative because you can't use 0. But it has to be a positive number. So when we graph this, if x has to be positive, which way do you think it's going to curve?
To the right.
To the right. Yep. So it curves to the right. And that graph, again, is not really what it looks like. Does anybody remember what's happening here, but the calculator can't do it?
It's going down.
Right, it's basically getting almost vertical. And I can show that to you if I go to the table and type in like 0.0000001 for x. I'm down at negative 23. So this graph is going down much further than it looks. The other way you can tell is, what does it look like it stops at?
-2.
Looks like it stops around -2. Well, zoom in right there, and then look at it again. Where does it look like it stops now?
-3.
Now it looks like it's going lower. So that's why it is going lower, but you can't see it unless you zoom in or check on the table. Let's just fix it. So it goes like that. And what do we call that? Because it's getting closer and closer to the x-axis. It's a vertical asymptote. Okay, so what is my domain in that graph? So does it go left and right forever?
0.
Right. Do we include 0? No.
I typed in 0.000 blah 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 1, and I still got a number.
I'm not sure what you mean.
Like on the table for the
Yeah.
lines, like I typed in that,
Yeah.
still got a number for what?
Yeah, I got a number 2.
Oh.
Negative 23. Yeah. Yeah, you get a number.
0.
The smaller you make this number, like the closer and closer and closer you get to the x-axis, the more and more negative it's going to go down.
Oh.
Yeah. If you plug in 0, that's a problem. You're going to get an error because you just can't do 0. And you can't do negatives either. If you could do 0 and negatives, the graph would be curving to the left, and it's not.
So it's just getting more and more vertical.
Right. It's
Getting
almost,
closer.
it's as steep as you can possibly be without being vertical.
A goat could climb on
Maybe, yes.
So the E in calculators stands for exponent, not what do you call it in that
Yes,
context.
this is a
Okay.
capital E. That is not
Not you.
No. That's just a scientific notation for 1 times 10 to the negative 20th power. Scientific notation. Okay, so our domain, 0 to infinity. How about the range?
all real numbers.
The range is all real numbers. The graph will go down forever, and it'll go up forever. Okay. Log functions do not have any horizontal asymptotes. It's just going to keep going like this. It's going to be slow, but it's still going to keep going up very, very slowly. So as you keep heading further to the right, the log function is basically as horizontal as you can possibly be without being horizontal. Okay, so range, all reals. If I give you any log function and ask you the range, it's always all reals. Doesn't matter how you shift, stretch, flip it, it always goes up and down forever. On domain, you can change. You can reflect that, make it go the other way, do all kinds of things. And that's what we're going to look at next. So every transformation that we've learned is exactly the same with logs. Nothing is different. Right, so let's start with the A and the B. The A and the B are inside the function. Okay, they're in the argument. What kind of transformations are always on the inside? The verticals or the horizontals?
Sorry.
The horizontals. So A and B are horizontals, and A is adding. So it's horizontal, and adding is a, what kind of transformation? Shift. Okay, so A is a horizontal shift. If A is a positive number, which way does it move? Positive is left. And if it's negative, it moves to the right. Yep. Now B is still inside the parentheses, so it's still horizontal, but it's multiplying, it's not adding. So when you multiply, what kind of transformation is it? It's a stretch. And remember, B is backwards, just like A. So if you have log of, let's do something like a log of 9x. 9 is a bigger number, but that's going to compress horizontally by a factor of 9. It's going to become 9 times more squished. If you want to stretch it 9 times as much, then you do log 1/9 x. 1/9, that's a small number. It's going to make the graph bigger. Okay? So big numbers, squish it. Small numbers, stretch it. That's only for horizontal. Okay. Any question on that? Right, now C. Okay. We're outside the parentheses, and we're multiplying. What kind of transformation is it when you multiply outside?
Vertical stretch.
That's vertical stretch. And what about when you add outside? Vertical shift. Okay, though vertical transformations are not backwards. If you add for D, if D is plus, it goes up. If D is negative, it goes down. If C is a big number, like 20, it's going to stretch it 20 times as big. If C is a small number, like 1/3, it's going to make it 1/3 as tall. It's going to squish it smaller.
When C is negative, which axis does it follow?
So when C is a negative, that can be your vertical reflection. And the axis that you flip over if you do vertical is the X. What about if B is negative.
Horizontal.
That's a horizontal reflection. Again, it's horizontal because it's inside. And when if you flip horizontally, that's left to right, which is over the y-axis. So there's 6 things that could happen. 2 shifts, 2 stretches, 2 flips. Any question on that?
Real quick, what's the order again?
In the order I wrote the letters. So horizontal shift, horizontal stretch, vertical shift, A, B, C, D. Okay, so this one says, how can log base 3 of negative x be graphed? And then once we graph it, we'll find the domain and the range just like we did on the last one.
So, what does the order mean? The order means like what? Which one would take effect first? Is that what it
Yes.
means? Okay.
Because if you apply them in a different order, you will get a different result.
Okay.
It's like PEMDAS.
Okay.
If you don't do arithmetic in the right order, you can get a different answer.
So is it the A, B, C, and D order?
Yes. Yep, alphabetical order. A, B, C. Okay, so let's look at this one. When you describe transformations, you would always compare 2 logs with the same base. You're not going to compare a base 4 log to a base 3 log. It's base 3 to base 3. How many transformations are happening in that one?
1.
Just 1. Okay, so let's start with that. That negative is really in what spot, if you look at the diagram? It's in the spot where B would go. If you want to think of it as a number, it's like having a negative 1x. What is that negative going to do?
Horizontal reflection.
It's a horizontal reflection. And that's it. That's the only transformation that happens. So we already know what the log looks like. When we drew it, it looked like this. If you reflect it horizontally, what's it going to look like? Which way would it go?
To the left.
Right. If you reflect it horizontally, it's going to look like that. So just by looking at that, we should be able to figure out the domain, the range, and so on. Well, let's start with the range. What's the range when you reflect it?
It's the same.
It's the same. You cannot change the range of a log function. It's always all real numbers. Now, how about the domain?
Negative to 0.
Right, that. Now it's negative infinity to 0, not including 0. Yep. And if you wanted to see, you could graph it. Just graph it. So instead of, we typed in log base 3 of x. If you want to do a negative, you can just press second, insert, and then you can put a negative in without retyping it. Yeah. If you don't press insert, it just types over what's already there. Okay, hit graph. Let's do zoom 6. And you're going to see it curves to the left. It's not going to show it going down because it's too vertical, but it should look more like that.
How did you change it without having it draw the whole thing?
I just press second, insert.
No, when it was like drawing the graph and you.
Oh, I paused it. So if it's in the middle of drawing, you can press second off and it'll stop. Then I don't have to wait for it to finish. If you press second off when it's not doing anything, well, then it turns it off. And, okay. All right, so we got the domain, we've got the range. The last thing they want is the vertical asymptote.
The domain was negative infinity to 0 with parentheses.
Yeah, that's right. Yeah, domain was negative infinity to 0. When you write the equation of something vertical, how does that always start? X. Asymptotes are equations, so you need to have an equal sign, not just a number.
So the domain for the one that we're starting from, without the negative, what would the domain be for that one?
The green one
Yes.
would be 0 to infinity.
It would be 0 to infinity. Oh, I see. I understand. Okay.
So, did the vertical asymptote change when we reflected it? No, because when we reflected it, it was reflected right on the asymptote. So what is the asymptote still?
0.
It's x equals 0. Yep. Now, the way it would have changed is if you shifted it. Let's say you did this. You shifted it to the right, and then you reflected it. So it would end up over there. This might have an asymptote at positive 3. Now this one is at negative 3. So if you do a shift first and then a mirror image, it changes the asymptote. Yeah.
Since the logarithmic function is just a mirror of the exponential function, could you use a transformation and turn a logarithmic into the same as the exponential?
So you mean like write this exact same thing as an exponential?
Kind
Yes,
of.
you could. The problem is you wouldn't be able to type it in on the calculator because the calculator has to have it solved for the y variable. So if you rewrite this as an exponential, it's 3. Logarithm always equals the exponent, and the argument ends up by itself on the other side. That's the exact same thing as that. Problem is you can't put this in on the calculator until you get y by itself. And the only way to get y by itself is to change it back to what you had originally.
I meant make log base of 3x look like 3 to the x equals y. 3 to the negative x equals y.
I'd make it look like it, but it would be the same.
So take this and make it, and do it like reflect it like a
Yeah, because it's a mirror of 3 to the negative x.
right. It's a mirror image over this line like that.
Yeah, could you transform it?
Yes. If you want to create the mirror image of something, all you have to do is take the x and the y and have them switch places.
Oh.
So, like something simpler. If you had this, if you had that, and you wanted to know what the mirror image of it would look like, it's that.
Oh.
Now you have to solve for y. And now if you graph that in the original, they would be mirror images of each other. So yeah, switching the x and the y will cause the reflection to happen. Yep. That answer your question?
Yeah.
Okay. You guys asked me good questions. I have to think. Okay. Any other questions on that one? Okay. All right, so another one. This time we are not doing the domain and range, just describing the transformations. Well, does what I just put a box around look exactly like the pattern that I showed you for transformations? No, we really should fix it so it looks more like what's on the left. What do we need to do to fix that?
Switch negative x to go to the front.
Yeah.
Positive 3, right?
So I would think of it like this. And if the transformations didn't make sense the way it was written before, hopefully they do now. Okay, so 2 transformations. What's the first one? Yep, we're going to shift left how much? 3. And the second one? It's a horizontal reflection. Which again, you could also say a reflection over the y-axis. So in this one, the asymptote would change. Because the first thing you would do is you would take the graph at the origin, you would shift it right 3, and now when you reflect it, oh, I'm sorry, yeah, left. You shift it left 3, same picture. So shift it left 3, and then when you reflect it, it ends up on the right side. So this is what your final picture would look like. Shift left 3, and then mirror image. questions on that?
Wouldn't it be kind of inverted because you'd be shifting that same first picture left, and then you'd be looking like this. It'd go around that way, right?
So it would fold like that.
But it isn't starting off that way. It's curving to the right.
Oh yeah. So yeah, it would be a little different.
Oh, so it would be like inverted.
Well,
Look like an upside down parabola. Right?
so if you shift it, let me just show you what it looks like. So it's going to look like log 3 minus x. Yeah, that's what it should look like. Except this part should continue down.
Okay.
So the original would have looked like, what was the original? Log of x. So it would be something like that. So the first thing you do is you shift it left 3, and then you fold it, and that's what it would look like. But that's what the final answer would look like.
Isn't that different from what you drew?
Yeah, I messed up.
Oh.
Yeah.
So it was kind of like inverted.
Yeah. So it should curve to the left in the final answer, not to the right. Yeah.
Sorry about that.
No, that's all right. I didn't think about it right. That's why sometimes it's easier to just sketch it on the calculator, then you can see what it looks like. And really, if you're trying to figure out what it looks like, you should just make a good sketch of it anyway, and that's what I'm going to show you how to do. If you try to do all the transformations in your head, like, all right, it's going to shift, it's going to flip, and then it reflects, like, it's hard to sometimes keep track of that. So to sketch a log function, one thing that's going to be very important we find is the vertical asymptote. Because once you find that, then all you really have to do is figure out, does it curve to the right from that asymptote, or does it curve to the left? So finding the asymptote is the most important thing. If you can find the x and the y-intercept, that's okay too. Does every log function go up and down forever? Yes. So then you're guaranteed to cross which axis? Guaranteed to cross the x-axis. But not every log function crosses the y-axis. Just look at this one. That log function never crosses the y-axis. So you will not always have a y-intercept, but you're guaranteed to have an x-intercept. Okay, so how do you find the vertical asymptote? Okay, take what's inside the parentheses. That's the argument. Take what's inside parentheses and set it equal to 0. That's how you find the asymptote. Now, once you find the asymptote, that's good, but you still need probably 3 other points to get an idea of how it's curving. You know, maybe like 1, 2, bless you, 3. Okay, three or so points will give you a good picture of the curve. Okay, and to find the x-intercept, you plug in 0 for what number? Think about on the x-axis, every coordinate has a y value of 0. So y is 0. To find the y-intercept, plug in 0 for x. Yep. So we've done that before with other kinds of graphs. And then I say, if you need more points, you will need more points. You'll need about 3. So we can just pick x's, and we can use the table on the calculator to get them. But remember, the log function is only going to curve in one direction. So if you pick points that go the wrong way, you're going to get errors in the table. Then you know, okay, I can't use the numbers I'm picking. Maybe use other numbers. Right. If your vertical asymptote is at like 2, you're either going to plug in values bigger than 2 if it curves to the right, or you're going to pick values less than 2 if it curves to the left. And normally, it always curves which way?
To the right.
It always curves to the right. The only way it can curve to the left is if you flip it somehow. Shifting it will never make it curve to the left. You've got to do a flip, okay, a reflection. So any question on that before we try a sketch? All right. So sketch a graph of that. Well, range we already know. You don't even have to look at the problem. What's the range of this log function?
All real numbers.
It's all real numbers. And the asymptote, you have to find that anyway to do the sketch. So you're not going to do the sketch without getting it. So you really got to do most of that anyway. Okay, how did I say to find the vertical asymptote? Take what and set it equal to what? Take the argument, set it equal to 0. So 3x equals -5. What's my vertical asymptote?
-5/3.
-5/3. Which is about -1 and 2/3. It's exactly -1 and 2/3. Okay, so that's your vertical asymptote. All right, let's sketch it. So when you are writing the vertical asymptote, it is helpful to know what the decimal is. -1 and 2/3. That's about -1.6 repeating. So that's where you're going to put the vertical asymptote. Let's put that at -1.6. Okay, so that's good enough. So now the domain is either going to be the numbers bigger than 1.6 or less than 1.6. Is there any reflection in that problem? No. Then which way is the graph going to curve? Right. It's going to curve to the right. So the domain is all the numbers that are bigger than the asymptote. So greater than 5/3. So let's put that in so we can just get a couple on the calculator quick. Log 3x plus 5 divided by log 2. And then go to your table. Okay, can you put 5/3 in, or -5/3? No, that's the asymptote. You're going to get an error if you try that one. So pick things bigger. If you pick things smaller, try like -20. No, the graph doesn't curve to the left. So you went the wrong way. We got to pick values to the right. So what's a good number that's to the right of -5/3? 0 is a good one. Yep. How about another one?
1.
Yep, you could do 1. And what? All right, we're kind of putting them too close together. We want to, because I can go all the way to 10.
5.
So yeah, I would go like 0, 5, and 10. And now that spaces them out a little bit. Okay, so 0, we're at 2.3. So I'd say about right there. We can do 1. Again, that's kind of, whoops. 0, 2.3, 1. I mean, it's okay. It's kind of close though. 5, we're at 4.3. 1, 2, 3, 4.3. And 10, we're just above 5. 1, 2, 3, 4, 5. Perfect. So now I can see the curve. Remember, it's going to go all the way down forever. All right. Getting closer and closer. And that's your sketch. Question on the sketch? And again, the domain is every number greater than 5/3. You could also write x is greater than 5/3.
Negative 5/3.
Yes. Thank you. Negative 5/3. Alright, so last question. So the last question is using a formula that we just plug into it, and it tells us the intensity of an earthquake. So R, that's the intensity of the earthquake. It's what we call the magnitude. A measures something about the earthquake called the ground motion, the vertical ground motion. And again, that's something they'll give you in the problem. And T is what we call the period of the wave, the earthquake wave. So if you imagine like standing at the beach, like a wave comes in every so often, however often a wave comes in, maybe every 40 seconds or something, that's called the period of the wave. It's kind of like, if, another way to think of it is if you were on a lake and somebody dropped a huge rock at the other end, like the wave is going to come towards you. Several waves. However often the waves are hitting your boat, that's the period of the waves. Maybe the boat gets hit every 3 seconds with another wave. They get weaker as time goes on, but that's the period of the wave. And B is the factor that accounts for the weakening. It's just like if you drop something in like a lake, the further away you are from where you dropped it, the less powerful the wave is. If you're right next to where somebody dropped it, you're going to feel the wave a lot more. So this is all stuff that they give you in the formula. That's just, B is a factor that accounts for the wave weakening as you move away from where the earthquake started. So if there's an earthquake in California and it's a really low magnitude, it wouldn't even affect us in Massachusetts. Wouldn't even feel it.
Are you sure?
Well, if it was
the next
weak.
one's supposed to be like really big.
Well, if it's big enough, you won't. But if it's small enough, you won't. Yeah. There's a chart online that goes through the different magnitudes, and there's like hundreds of earthquakes that happen every day. Just a lot of them are like magnitude 1 or lower, and they might be in an area that nobody lives, like in the middle of the ocean.
Underground volcano.
Okay, does everybody have the descriptions of what goes in the formula? All right, let's try an example. Okay, so find the magnitude of the earthquake. All right, so let's say that A is 250. So that's how much the ground is moving in micrometers. That's not a lot. 2 micrometers are very small. 250 micrometers. The period of the wave, let's let that be, 30 seconds. And the factor that accounts for the weakening of the wave, 4.5. So let's find the intensity. So the letter I use for intensity is R. And what's the first thing that comes on the other side of that formula? Log. Yep, log. Okay, what goes in the top?
250.
250. And the period
30.
is 30. And then what goes on the end?
4.5
Times 4.5?
plus.
Plus. Okay, so let's see what the magnitude of that earthquake would be. So log of 250 divided by 30 plus 4.5. Okay, so that's a magnitude 5.4 earthquake.
Is there a reason you had to do those separate?
No, I probably could have done it all in one step, yeah.
Or
How does the 4.5 make it weaker?
What is it?
How does the 4.5 make it weaker?
Well, the 4.5 is a number that accounts for, like, I guess the material in the ground. Maybe if, like, it's in the middle of the desert, I would think sand would absorb the energy of the earthquake more. Like, if you drop a rock in sand,
Okay.
you don't really get much of a wave. But if you drop a rock, like, on like concrete, and you put your ear even, like, 30 feet away on the concrete, you'll feel it, you'll hear it, because the concrete is solid.
Huh.
So I think if the ground is more solid, the energy travels easier. Okay. So the homework is page 301. And it's those 10 or 11 questions. 11. Okay, I will also put up a list of topics that will be on the test, and I will be after school today.